Hello, everybody. So what we're going to be looking at today is the end of section 2.1 and hopefully all of section 2.2. Both of those sections are about sets. So let's go ahead and get started. So let's see. I think where we left off last time is we had just done talking about subsets and we had mentioned the empty set. So we're going to talk about subsets. So let's remind you of what those are. So we would say definition, um, A is a subset of B. So A and B are both sets. If and only if, they use if and only if, by the way, just to indicate that this is in fact the definition of subsets, not just a property that subsets happen to have. So A is a subset of B if and only if for all X, if X is in A, then X is in B. So hopefully that is the definition. I think it is. So there you go. That's the definition of subsets. Okay. And remember that the basic idea here is just that if A is a subset of B, then A is inside of B. So what do I want to say here? So let's just have the notation is like this. And then the idea is every element of A is an element of B. Also an element of B. Okay, and that's a subset. And then after we had that, we talked about the empty set. But not before. Let's talk about the empty set. So the empty set is this. We had another definition. The empty set, denoted this way, is a set with no elements. So there's nothing inside of the empty set, hence the name empty. All right, so that's the empty set. Here's a theorem from the book. I didn't call it a theorem in the last lecture, but I will now. So for every set S, so every set has this property. Well, there's actually two properties. So the first property is that the empty set is a subset of the set. And the other property is that the set itself is also a subset of the set. Okay, and I'm not really going to prove these, but so the idea of the proof is something like this for these properties. So so first of all, for the first one, every element of the empty set is an element of S, right? That's what it means to be a subset. I'll put a question mark on that. Is that true or is that false? Well, that's true, right? Every element of the empty set is an element of S because the empty set doesn't have any elements, right? So if you wanted to prove this incorrect, if this was not true, so for this to be false, there would have to be, so if this was going to be false, there would have to be an element of the empty set that was not in S. I'll say is not in S, not was not, is not in S. Now, of course, there is no such element, right? There's no elements of the empty set that are not in S because there are no elements of the empty set. So, of course, this is impossible. Right? So that's kind of for that first one there. Now, that's not really a proof. I mean, I didn't formulate it as a very methodical proof, but the idea is there, right? Now the second one says S is a subset of S. So of course that's also true because is this true? Um, True, obviously. Obviously, every element of S is also an element of S, right? No matter what S is. So these two properties here in the theorem are just, you know, pretty straightforward, but they're worth writing down because of something that we're going to do pretty soon here. Okay, so I want to mention them. Okay, so the next thing I want to talk about is equality of sets. Now, we already, I think, had a definition for equality of sets, but here's a slightly different definition of equality of sets. So um, let's see. This isn't, I guess, not a definition here. This is just an idea. But let's see. To show two sets, A and B are equal, you can show that A is a subset of B and B is a subset of A. Okay. I don't have anything to say about that right now, but if you don't know how to show two sets are equal, that's how you could do it. You could even use that as a definition of equality. We had an earlier definition of equality that said, like X is an element of A if and only if X is an element of B. But this does it without talking about individual elements. All right, next thing. So this is kind of really the first new thing in this section. I went over the other stuff pretty quickly here because it was in the last lecture. But this is what we want to get to. So size of sets. Sizes of sets. Okay. Now, you'll see this in other math classes too, and it will be called cardinality. That's in it. Cardinality. All right. What is it? So, well, here's the definition. We'll write the definition and then you'll know. So, let S be a set. All right. If there are exactly indistinct elements in S, where n is a non-negative integer. So just note, you can't have negative number of things. So S is a set if there are exactly n elements in S, or n is a non-negative integer. We say S is a finite set and that n is the cardinality of S. All right, so let me highlight a couple things here. So let's see here. So we have a finite set and we're talking about cardinality. So specifically, n is the cardinality, and that's if there are indistinct elements, right? Then n is the cardinality, right? And so this is just a fancy way of saying, so if it's a finite set, so if a set is finite, just the cardinality is just the number of elements. So you just count. right? So that's the idea. Cardinality is just number of elements. So it's the size of the set. Now, the reason we call it cardinality and not just like the size is because in other disciplines of mathematics, we would want to have different kinds of sets that have an infinite number of elements. And so that's why they don't just say size or something like that. Let me just say that. Um, so we don't say size or something because in other classes, actually, this like you could find it in this book as well, but we're not going to get to that section. It's way later on in the book. But we don't just so we don't just say size because in other subjects um, we have infinite sets, and actually we have to know the difference between different kinds of infinite sets. So we have names or words that we use to describe, I should say, um, words to describe uh, the number of elements, or I shouldn't say that, but to describe the size of sets. And there's different kinds of infinities is basically the problem. There's different kinds of infinite sets. And so they want to be able to talk about different kinds. And so they want to use different words to describe the different kinds of infinity. And so that gets complicated. And so they don't just call it size because there has to be a precise definition of what cardinal or the cardinality of a different kind of set is. So you couldn't say, like, oh, what's the size of it? Oh, it has an infinite number of elements. Well, cardinality is more complicated. That you can't just say an infinite number of elements. Okay. So yeah, just kind of you don't have to pay attention to that. It's basically what it comes down to. But I mean, you should know this. So a set that is not finite is called infinite. That should be reasonable, right? So that's all we're going to do for an infinite set. We're not going to have different cardinalities of infinite sets. Okay, so yeah, we've got, what do we have? Two more things in section 2.1. So the two things we have in section 2.1 is going to be power set. Let's talk about power set. Power sets and Cartesian products. Power sets. Guess I don't need a colon. So, definition, what is a power set? So a power set is you have a set, first of all. So given a set S, the power set of S is the set containing all possible subsets of S. All right. And the way that you write it is so the power set of S. How do you write it? Like this. So it has sort of a scripty looking P and then an S or whatever the set name is. So power set is just P of S. Okay. Um, Now we're going to find one of these and then I'm going to make a note about the number of things inside of the power set. So let's do an example first so we can get used to this idea. Find P of S, so script ES, where S is going to be the set ABC. Okay, power set. So the way you do this is you're going to have to list every possible subsets. So what you do is this. So we need to write out a set that has as elements one, every 0 element subset of S, every 1 element subset of S, every 2 element subset of S, and finally, every 3 element subset of S. Right? Now, why are we doing that up to 3? Well, because of course S happens to have 3 things in it. If you had a set with 5 things in it, then you would have to go all 0 element, 1 element, 2 element, 3 element, 4 element, 5 element subsets. Okay, so power sets tend to be big. There's a predictable number of sets in the, there's a predictable cardinality for the power set of S. But I want to do this one example or maybe 2 examples before we write down what that is. So how do we do this? So let's say E of S. What is it? So it's a set. So open the set. And now the elements are subsets. So that means we're going to have curly braces in our curly braces. So let's see. Let's do these. So first thing we need is 1. Every 0 element subset of S. So what's a 0 element subset of ABC? How about that? Right? Because remember what we said up here somewhere. We just wrote it, but I boxed it, didn't I? Yeah. So remember, the empty set is an element of is a subset of every set, and also S is an element of every set S. So those are the 0 elements and the, I guess, 3 element subsets for us. So the 0 element subset is the empty set. So you're actually going to have an empty set in every single power set, right? So this is the 0 element subsets. All right, move on. Now we need next the 1 element subsets of S. So how many of those are there going to be? Well, look at S. S contains A, B, and C. So if you want 1 element subsets, then a subset of S that has 1 thing in it would be like a subset, so curly braces, A. That's a subset of S that has 1 element. But that's not the only one, right? There's 2 others. So the next one is that, and the third one is that. So these are your 1 element subsets, right? One thing in there. Now we move on. Now we need every 2 element subset. So that's going to be every combination of 2 things out of S. So every combination of 2 things. So for ABC, you're going to need an A and a B. That's one of them. You're going to need an A and a C. That's another one. And then you're going to need what's missing, a B and a C. And then there's your 2 element subsets. You need to get every combination. So 2-element subsets. Last thing, every 3-element subset. Well, S only has 3 elements, so the subset with 3 elements is actually just ABC, the original set. And then we're done, so we can close that set. Now, if we count up the number of things in here, let's see what we have. We've got 1, 2, 3, 4, 5, 6, 7, 8. That's the right number. Okay, I'm going to write it right now. I was going to write it later, but I'll write it right now. So let's see. If the cardinality, oh, by the way, I kind of made a mistake. Not a mistake, but I didn't write the symbol. So let's back this up and talk about where we talked about cardinality here. No, I don't have room. Let's do it right here. So if the cardinality of S written this way, like absolute value symbol means cardinality. So if the cardinality of S is in, let me actually move this over a little bit, so I can say it in words. Right, so if the cardinality of S is in, so absolute value of S equals in, then the cardinality of the power set E of S is 2 to the n. In symbols, like that. Okay, and so that is useful because you're going to have to write down power sets as part of the homework and also probably in your test. And you need to know how many things are in the power set. That way you can make sure you don't miss any, because it's really easy to like lose one of these or something if you've got, more than 3 things in your original set. Yeah. All right, let's try some more of these. So something that is kind of confusing is when you have the empty set as part of your set. So let's try one of these. Another example, switch colors here. Find E of S, where S is what? We're just going to put 2 things in it though. We're going to put the empty set, and to mess with you, a set containing the empty set. Okay, so this is going to be kind of dumb, but it's the kind of dumb that the homework is going to be. So get used to it. All right. So before we start, how many things should be in the power set? So before we start, note the cardinality of S. How many things are in S? 2, right? There's 1 and there's another 1. 2. So how many things should be in the power set? Right? So the cardinality of the power set should be 2 to the 2 or 4. So our power set should have 4 things in it. And if it doesn't, then we messed up. Okay. So that's why it's good to know how many things are in there so you don't screw it up. So let's try it now. So what is the power set? So the power set for S is, all right, how do you start this? So remember, we need all 0 element, 1 element, and 2 element subsets. We don't need to go higher than 2 because, of course, S has 2 things. So what's the 0 element subset? Of course, it's the empty set. always start with the empty set, right? After you have that, then you have your one element. So what are your one element subsets? Well, you need to look at what we did on the previous one. So like when you're doing the one element subsets, you need curly braces around an element. So you need curly braces around this element to get your one element subset. So that's one of your one element subsets. Now, after you have that, you need to put curly braces around this element. So the next one element subset is actually got two curly braces in there. All right. Now that's confusing. I know it is. But so what's happening here is that this is or I'll say the set containing 0 elements. The set with no elements. This is not the set with no elements. The next one is this is a set with one element, and that one element is the set with no elements. Okay. And then when you put two sets of curly braces around it, that's a set with one element again, but that one element is the set containing the set with no elements. Okay, so that's very confusing, right? But remember that the one with no curly braces, this right here, this is already a set. So this is a set in a set. And here, this is a set in a set in a set. It's an inception. Nobody laughed. All right, let's go. So we have these one element subsets. Then you need a two element subset. Two element subsets. And so the two element subset here is just going to be the full original set. And then we're done. So you close the power set. And if we did this right, this should have 4 things in it, right? So you've got 1 set, 2 sets, 3 sets, 4 sets, right? So that's the 4 that we're talking about there. And yeah, that stuff with sets containing set is pretty confusing, but it is what it is. Okay, so it'll be in the homework and you can come to office hours for help with it. All right, let us move on. The lag is driving me crazy, so I am opening the Note app again. Okay, there we go. Nice and lag free. All right, so last thing in section 2.1, Cartesian products. So the Cartesian here is like the Cartesian plane. The Cartesian plane is the XY plane, and you'll see why pretty soon. So let's see here. So let's see. Definition. Do I like their definition or not? No, okay. Definition. This is their definition. So let A and B be sets. The Cartesian product of A and B which you write this way, a times b with the x multiplication symbol, is the set, and here's how the set is made. So it's the set of all xy, no, they say ab, the set of all xb, ab, where a is from a and b is from b. And you can write that in symbols this way. You can say a cross b, or a times b, is, and we can use set builder's notation, the set of all AB such that, that's not the symbol I want, A comes from A and B comes from B, right? That's the definition. It sounds more complicated. It sounds more complicated than it is. I'll show you with an example that this is actually really simple. Example. Let A equal ABC, and B is going to be like 1, 2. That's it. Okay. And I want to find, we want to write out A times B, the Cartesian product. Okay. So how do we do it? So here's what you do. It is a set. Every element is an ordered pair. Everything is an A comma B in parentheses, like ordered pairs like X comma Y. Okay. And what you do is you just get the first element comes from A, and the second element comes from B. So if B is here and A is here, you're just making ordered pairs out of the A, B, C, and the 1, 2. So what's it look like? Looks like this. So your first element comes from set A. So it could be a little a. Your second element comes from B. So it could be a 1. That's a possible element of A times B. Now, what are the others? Well, you could have A and 2. That's another possibility. You could have a B and a 1, or a B and a 2, or a C and a 1, or a C and a 2. And that's the whole thing, right? So the deal is your first element comes from set A, and the second element in the pair comes from set B. And that's the Cartesian product. Okay? Now you can do a Cartesian product of a set with itself. For example, I could do this. I could say let t equal 1, 2, 3. That's supposed to be a 3. And then I could say find e times t, like that. And that would be the set of ordered pairs. So it's still pairs. It's still pairs, but you pick the first element and the second element from here. 1, 2, 3. So all of the ordered pairs that you can make out of 1, 2, 3 are going to be like 1, 1, 1, 2, 1, 3. That's 3 of them. But then we can change the first element to a 2 and have 2, 1, 2, 2, 2, 3. But then you can change the first element to a 3 and have 3, 1, 3, 2, 3, 3. And that's probably all of them, right? So that's what a Cartesian product is. Yeah, it's called Cartesian because like you can have the XY plane. So like in calculus or algebra or anything. So in calculus, um, we know that you know what the real numbers are, right? Um, you know this is the set of real numbers, of course. Um, what this means is that, so if you wanted to look at R cross R, um, is the set of all x comma y, where x is a real number, so x, I should say, is from R, and y is also from R, right? And so that's actually every point on the xy plane, right? So I'm just going to put some points on the xy plane, right? Every point on the xy plane is an element of R times R, R cross R, the Cartesian product of R and R. Okay, so you got the xy plane. So you've dealt with Cartesian products before, and also um, the xy plane is also called the Cartesian plane. Okay, so yeah, so that's what a Cartesian product is just ordered pairs. Okay, now you can extend this on to um, higher products, I guess. So you can extend this. It can be extended easily, so that, for example, A cross B cross C. Let's even go further. Let's go D. A, B, C, D, for example, is the set of ordered, what would you call those? Quadruples? That's probably wrong, but that's what I'm going to write. I'm going to write quadruples. Um, Probably got some weird name that's not that. So like example, so like A, B, C, D would be the set of all X, Y, Z. Actually, maybe I'll change those to A, B, C, D. A, B, C, D. So it's like that now, such that, well, you have to get the A from the A, and you have to get the B from the B, and you got to get the C from the C, and you got to get the D from the D, like that. And I did 4 there, but you could have done 3, or any number. Okay, and so that is a higher degree, not degree, but higher dimension Cartesian product. Okay, let's see. I believe that's everything I want from this section. So let's go on and we can finally move on to section 2.2. All right, so section 2.2. What's in section 2.2? So section 2.2 is set operations, and we're not going to do very much of this, I don't think, but we'll do some. So I think you're going to know some of this stuff. We're going to be talking about unions and complements and that kind of stuff. Um, Actually, you know what? I'm looking at this right now. We are 40 minutes in, and I'm only just barely getting ready to start section 2.2, which is not a tiny section. So let's skip it. We'll do it next time. All right. So that's it for now. Next lecture, next time.